if I measure all the omega naughts out for a medium, I will have a good idea of things. So, spectroscopy is all we need to know. Determine all the omega naughts and you are really doing fine in terms of knowing about the medium. Okay. So, but that is not obvious from whatever I have said so far, it is just something I am stating as a matter of fact, but we have simplified this entire equation in writing P's linear dependence on E as being mediated by chi. Of course, epsilon naught is just incidentally there, it is a choice of how we wish to write it. Chi is called the susceptibility of the medium. In this case, we are describing linear interactions. So, this is the linear susceptibility of the medium of interest. Right. So, it is in this sense that we can now write for the linear case the inhomogeneous wave equation. Inhomogeneous meaning the del square on the left minus 1 over the square of the velocity of the electromagnetic wave. Okay, in this case it is C naught, the velocity in vacuum, times the second derivative with respect to time. This 0 was the homogeneous equation. In terms of the equation is inhomogeneous because on the right hand side we have a source term, okay, and the source term is now identified to be P is epsilon naught chi e for the linear case. So, I substitute for P here as epsilon naught chi e, okay. The mu naught here helps me to reduce the coefficient on the right hand side to 1 over the square root of 1 over the square of the in vacuo speed of light C naught, okay. And I have now a very nice homogeneous equation for the propagation of light back in this medium, wherein the only modification that has happened is this numerator term. Instead of 1, it has become 1 plus chi. The medium has no free sources, no free charges or currents. The medium only has dipoles, dielectric. It is a neutral medium, electrically neutral medium. Okay. Typical glass, typical of lot of media. Okay, you can ask me if the medium has any particular color. For now, I would say let us not go there. We will be able to understand that soon pretty well. But if it is a transparent dielectric like glass, it is a very good picture to have in mind while discussing this physics. Then 1 plus chi is in the numerator divided by the in vacuo speed of light, here we call it C naught square, right. So, then I will make a little leap because we have already seen this bit in our earlier discussion. For the 1D wave, we have seen here v is the velocity. If you wish for a monochromatic wave, the phase velocity in the medium, here one over v square is equal to 1 plus chi c 0 square, what we used to call c square, the speed of light in vacuum, right. So, therefore, since we know that v is c by n, n being what? The refractive index, n is the square root of 1 plus chi. Of course, you can associate chi is dependent on frequency because x e was dependent on the driving frequency and omega, the refractive index will also depend on frequency. So, 1 plus chi is the square of the refractive index. Here the real part of the refractive index, if you want me to be very rigorous, because I have not considered absorption and stuff like that in this discussion yet, explicitly at least, right. So, 1 plus chi is the square of the refractive index. So, chi is just a family member of refractive index so far. Okay. So, now if we solve the homogeneous equation, we can figure out the same fact over here. So, let us even do this gradually, take a couple of minutes to do that. Take the inhomogeneous wave equation, I am still calling it inhomogeneous because the source term is implicit in the left hand side, it is embedded in the left hand side through the chi. Okay. This is just the velocity of light. So, here we are using C naught for the in vacuum speed of light in vacuum, and C for the velocity of light in the medium. Okay. And so, C, the velocity in the medium is the vacuum speed divided by the square root of 1 plus chi, merely by interpreting the coefficient of the second derivative in time, as we should for the wave equation. And we can Taylor expand this if you wish, and the square root of 1 plus chi can be written as 1 plus chi over 2 for the leading order term for that matter. It is a simplification. Now, we can then, as a consequence of the fact that we now have identified C to be C naught divided by 1 plus square root of chi, put all our knowledge of the wave equation and write down simple solutions such as the harmonic solution. E of z is E naught exponent of I k z minus omega t and the such, where k then becomes omega by c and so on and so forth. Substitute for C over here and write C to be C naught divided by 1 plus chi, okay, and therefore, k naught times 1 plus chi by 2. Now, chi in general can be complex. Why? Maybe a simple answer is why not, but we know why, because if I allow chi to be complex, then I hit two birds in one stone. How so? The imaginary part which has an I associated with it, the imaginary part which has an I associated with it comes out to be E naught times exponent minus something by 2 times z plus exponent I, okay, exponent of I with k naught multiplying 1 plus half the real part of chi being the important thing here, times z, bless you, minus omega t. If we take this seriously, then we should compare this to an expression which we had earlier, and help me recall this correct. We had minus alpha by 2, sorry, let me write my 2 properly, z exponent of I k naught times n times z minus omega t. So, you see we now can relate the absorbance alpha to the imaginary part of chi by simply allowing it to be complex, whereas the refractive index, as we already did, okay, to be 1 plus a half of the real part of chi with a tiny error, but we can always take the square root and stuff like that. So, chi because it is linear, let us put a 1 there, linear. So, this is the electric susceptibility, the linear part of it, but it has a frequency dependence and it has a real part plus an imaginary part, right. So, this captures with Maxwell's equations all, I stress all phenomena in linear optics. The only thing I may want to add is linear classical optics. Okay. All you know and all you need to know as far as linear optics is concerned. The rest is we need some imagination and physical insight to solve problems or talk about media that correspond to this. Okay. Now, we will just make a quick note on absorption coefficient and refractive index, which I already brought about. We connect the imaginary part of chi to the absorbance by defining alpha to be k naught times chi. Maybe I missed a k naught in my previous description, but please take a note, and n is 1 plus a half the real part of chi. Okay. This is k naught times alpha is k naught times the imaginary part of chi plus refractive index is 1 plus a half the real part of chi. Okay. So, sorry, the vector thing has somehow come down. I should check my slides on the same machine, I think. So, do the substitution and we have recovered, you can say, the entire thing about linear optics in this case, okay, by putting all these things back into the original framework. The wave equation with the speed of light now being c naught by n or c naught by 1 plus a half the real part of chi, and therefore, now we can go back, we will rejoin here in the next class, which is next week, right. And now we have actually this really nice insight, because we knew about the real part of x of t, we had the real part of x of t. What is the real part like? The real part was like delta divided by delta square plus gamma square plus I times, am I right about? Pardon me? Gamma divided by? Oh, that is the real part? No. What is the real part? 1. No, delta. This is delta, and the imaginary part also has this in the equation. What is the numerator? This has to be even, an even function. Is it gamma? No, it is delta square. Can somebody check this for me otherwise? Okay, it has to be a square, that is all. Okay. Either way, the point being that we knew that the real and the imaginary part have this relation, but then chi linear chi got its time dependence from xc of t, and so the real part of chi should behave like the real part of xc and the imaginary part of chi should behave like the imaginary part of xc. Okay. So, therefore, and since refractive index is 1 plus a half the real part of the linear chi, refractive index should have this sort of frequency dependence, this Z shaped curve, whereas absorbance, the frequency dependence of absorbance turns out to be k naught times the imaginary part of chi 1. It should have the frequency dependence of the imaginary part of xc of t. This has frequency dependence of the real part of xc of t, and so this is essentially going to have the same functional form as here. Okay, this guy. This is why absorption is always associated with a peak structure. Absorption is a peak. So, the nice thing about this approach to absorption coefficient alpha and refractive index is we have not made any assumption about what the medium is. Is it glass? Is it even a metal? Is it even it's a gas? Is it some liquid? The only assumption we made is the interaction between light and matter is linear, and that in this case there is a displacement of the electric field, the electron cloud creating a dipole. But I will close this lecture with a small insight or whatsoever you may call it. If we can generalize this beyond the displacement of the electron cloud, away from the nucleus. We can generalize this. Why? Because what mattered to us was just the time dependence of the dipole moment per unit volume, right. Now, how do you care what type of dipoles these are? How do you care? How do I care? I do not care. What these dipoles are? Are these dipoles created out of motion of the electron cloud? Is it specific only to this, or could it be a water molecule carrying a permanent dipole moment P, right? Oxygen grabs electrons more towards itself as compared to hydrogen, say electrochemistry. So, there is a permanent dipole moment to water. So, now this dipole can be made to rotate. Suppose I can spin this dipole around. This can have this is also a sinusoidal oscillation of P naught. It is an oscillator, but it is coming out of the rotational motion of the molecule. Let us say this has an eigen frequency omega naught. So, this eigen frequency omega naught is about 3 gigahertz. Okay. So, therefore, I can use the fact that water has this rotational eigen frequency at 3 gigahertz, it rotates. So, I can open the door of a gadget, throw some stuff, close it back in and pop my popcorn. It is microwave. This is your microwave oven. It works because water molecule has a eigenfrequency of 3 gigahertz. You apply 3 gigahertz from a klystron source. So, if you have a microwave oven, please take off the lid and see what is inside. You have a klystron source, but be careful, do not turn it on, it is not, it is harmful. You can actually see a Faraday cage inside a microwave oven next time you look at it wherever, right. But the point being that the dipole can also come out of rotation, okay. Or if you have a hydrogen molecule H and H, you have electron cloud, no basic bond with the most simplest molecule, this is an electron cloud. Now, this can vibrate, or you have C double bond O. So, this is again to delta minus, it is, this has no net dipole moment, but if this C came closer and this C went away further, I am just struggling to draw this here, then here you have a dipole like that and here you have a dipole like that. This is your dipole moment. So, then the molecule is vibrating asymmetric. So, what do you have as a consequence of this? One of the factors, you have global warming due to that. Again, it is oscillating dipoles. So, this is rotation. So, rotating dipoles are the basis for popcorn, which we need to watch movies this weekend, and vibrating dipoles are the cause for the fact that when we sit in the movie and turn on the air conditioner, we are heating the planet up catastrophically. So, maybe it is a trade off, should I go to a movie this weekend? On that question I will stop my lecture and take some questions.